Picture of Tennessee. The blue star is actually where we are now, but it's also where I was born and raised. That's Nashville, Tennessee. I obtained my BS degree in physics from Rose College in Memphis right here in 2006. I then joined the Vista Vanderbilt Masters of PhD Bridge program in 2006 as well, back in Nashville. I got my MA from Fisk in that same 2008. That's me right here. I also then crossed the bridge and joined the physics department over here at Vanderbilt in 2008 as well. In 2009, I joined the Institute of Imaging Science, right here, actually, in the back, tall-ish. Then I gained my PhD candidacy, I passed my qualifying exam in 2011, and I have my prospectus accepted in 2012. So that really means I'm going to finish up in the next few years, hopefully. But anyway, I do want to make it in the bud now. Breast cancer is bad. Just no ifs, ands, buts about it. It's bad. It has some really bad statistics about it. I could talk about it all day, but here are some of the big ones. It is the second most common cancer among American women, followed by lung cancer. 1 in 8 women will actually contract or develop it in their lifetime. And it is currently the leading cause of cancer death among aging women. And so X-ray mammography is currently the only screening tool that we use to detect these. And mammography does work great in their instances, but not in a very specific population. If you happen to have very dense breast tissue, which is typically in women who are much younger or a little bit more well-endowed, your ability to measure small tumors with mammography is extremely low. At the same time, you cannot distinguish between benign, which are usually like skin molds and things like that, the ones that aren't so harmful, and malignant, the ones that are very aggressive, the ones that grow very quickly, the ones that will spread throughout the body, the ones that are really harmful. And you can't make this distinction. If you can't do that with this tool, then you're going to make some false positives. Your doctor is going to look at those images and say, oh, I think there's disease here, when there really isn't. And so they have you go in for this biopsy where they take a long needle and stab you with it, trying to get a little bit of the cells, the culture. And that can lead to further complications, surgical costs, and it can give you a lot of grief and stress. I mean, if they tell you you have a disease when you don't, that's pretty stressful. So what can we do? What other options do we have at our disposal? So here is the imaging Triforce. Triforce is copyrighted by Nintendo, but I like it for this instance of the different options we have for imaging. And so what we have are these 3 properties that describe any sort of imaging modality or just type of imaging you can do. Resolution, just telling you how small you can see something. Depth is how far into an object or a person you can actually measure. And sensitivity is essentially the information, how much signal you can get above your noise. Okay? And so we have ultrasound, which we're pretty familiar with. It has good resolution and sensitivity, but not really great for depth. So we can see babies with this fairly well. Ultrasound uses sound waves. We have MRI, which uses radio waves and magnets and proton spins to formulate images. And it has great resolution and depth, but not so great with sensitivity. And X-ray, that's Homer's favorite picture of mine. X-ray, this is where mammography currently sits. It has pretty good resolution and depth, but it doesn't have that good sensitivity. It doesn't have that ability to distinguish those benign or malignant tumors that I mentioned before. But then we have these PET or SPECT, these nuclear options, that uses a drug that has a radio tracer or a gamma rays that are emitted from it that accumulate in this malignant tissue, but doesn't really accumulate in benign tissue. And so we can use this as a tool to image these smaller tumors in women with particularly dense breast tissue. And so this is what the transition I'm trying to make. But what's currently holding us back? We have the modality. There are already systems out there that have this ability. You can see that in this image on the left, you have a regular mammogram result, and you can't see where the tumor is here. But that same woman had a different scan using nuclear breast imaging, MBI, and you can clearly see where the tumor is here. So what's the deal? Well, currently, X-ray mammography is FDA approved. It has a very low cost. It works great for the general population, and you have a very low radiation dose. And this is really our issue. And that's what's keeping it from becoming FDA approved. It is more expensive because you do have to inject drugs and take those in to have this accumulation. And it has this really high radiation dose. And what that means is that gives you an opportunity or a chance to actually induce disease in your patients. And that's not what we're about. So what I want to do is I want to improve breast imaging by designing a highly sensitive system, a system that will be able to find this disease if you don't inject so much radiation. So if you can get to a level where you're only injecting the same amount of radiation you get from a mammography scan, that would be really great. And so that's what my work is. So the 4 easy steps. Here comes some of the meat of my talk, and it's quite simple. This is it. This is all you have to do. These two up here essentially is making a camera, something to image your object, image the system. So your radiation detector, which is your film, you can think of it as your film. Your collimator, which you think of as a lens. We can't really bend gamma rays, but we can collimate them so they can only follow a certain path. Then you have to find a protocol, a way to take a 2D picture, and you can think about how many pictures you want to take. And then your image processing, which you can take all of these 2D pictures, or one picture, and generate a 3-dimensional image of your object or the patient. So I want to talk about these steps individually. You have to first select your film. And so I've decided to pick, well, my advisor really, has decided to pick germanium detectors for these 3 reasons. They have very desirable properties. Energy resolution really leads to our ability to eliminate scattered photons. Germanium has the best energy resolution of any camera that you could ever find. And what that allows you to do is eliminate scattered photons. Photons that have scattered in the body have lost all information, position information of where they came from. So you can't use those. Those are just going to add to your noise. And you want to be able to weed those out, which you can do with germanium. You have pretty good spatial resolution, so you can visualize the smaller tumors. That's what we want to do. And you have pretty good depth estimation within your detector. And what that gives you is ability to measure depth within your object. And we can obviously now finally build these into compact systems. This is a system that I helped design. The company that made it is PhDs in Knoxville, Tennessee. They actually grow the germanium for us and design all of this. But I helped them design this part, which is the collimator, which I want to talk about next. So here's the collimator here. And there are different things you can do with this. There are different types. Here are some of the different hole shapes you can have. This is hexagonal or square. You can also make them out of different materials. This top one, is the standard that's currently used. It's made out of lead and it's hexagonal hole. This one is actually a better fit for detectors. This gives us a lot more sensitivity. And here are some of the parameters where it can adjust. What I've decided to do is increase the D, which is your hole size. This T is also smaller, so it's less material, so it's a lot cheaper to make them. And this L is also shorter, so it's less material, cheaper to make. And this C, we can't really adjust so much. Well, by adjusting these properties, you can actually increase your sensitivity to detecting disease, while still maintaining a bit of good resolution. All right. Step 3, you have to take your picture. Here's a schematic of a patient that is undergoing a similar scan, and so we're going to zoom in on this region, the region we really care about. And so what I've done in my work is model this using Monte Carlo simulations to really see the performance we could get if you use the current standard, which is actually a cadmium zinc telluride detector, versus using germanium. And so this is my model here. It's just a side projection or side view. So this is the heart right here. It looks like a box, but it's really cylindrical in shape. The liver right here is also cylindrical, but in the orthogonal direction. This is the torso, and this is the breast here with 3 spherical tumors. And so what I've done in my testing is I've taken this camera, this is where our collimator is, and this is where the detector lies. All I've done is I've replaced the detector, which was originally CZT, with germanium. And I've run the same sort of model going forward to generate images. And here are the images that we've generated. Here are my results, essentially. So this is the current state of the art. This is what people have been able to do so far with breast imaging. And this step right here is just replacing the CZT with germanium. And you can definitely see that these tumors look brighter, but you also get increased brightness in your background. Finally, when I actually apply a processing step to actually gain this 3-dimensional image, this is actually just the same sort of picture. I've just summed it, projected it into 1 dimension, so you could into 2 dimensions, so you can see it just similar to these. And you can clearly tell that your background's a lot smaller, but your tumor is still bright, so you can still see these. And you can still do this by injecting less radiation, by running less photons in the model, and you still get just as good performance. And that's really all I have to say. That's the final step is always to acknowledge your people. This group over here are the people that work in my lab. This is the CEO and president of PhDs who we've been working with. I want to acknowledge my PhD committee. And with that, I'll be happy to take any questions.